Now the problem I'm doing, it's called maximum range of block falling from inclined plane. So you have a block that starts with from initial height capital H. It goes down an inclined plane. The shape of the inclined plane doesn't matter. There's no friction on the inclined plane. The final height of the inclined plane is small h. So the question is, what should small h be? What should h be so that the block has the most maximum range? Okay, so what should the value of this be so that the block goes the furthest possible distance? Okay, so the reasoning behind this is that if h is too large, what's going to happen? This one is going to go like this, but because the two heights are equal or somewhat equal to each other, the initial velocity of the block is going to be low, right? It's not going to be traveling too fast, so that even though it's high, because it's not traveling too fast, it will immediately fall down and hit the ground, right? If the h is too small, what will happen? Now, the block will be traveling faster, right? It's traveling really fast, but because it's so close to the ground, even though it's traveling very fast, it goes and immediately hits the ground. You see? So there's a balance that's struck here. If the height is too high, it doesn't pick up enough speed. If the height is too low, it picks up a lot of speed, but because it's close to the ground, it hits the ground immediately, right? So how do we calculate that? Well, we can come up with an expression for the velocity that it has here. We're assuming that the initial velocity is 0, right? So if the initial velocity is 0, what would be the equation for the final velocity? Final velocity would be a square root of what? The final velocity will be the square root of the difference of the heights, right? 2 times g times the difference of the heights. 2g h minus h, because that's the effective distance that the block is going down from its initial height to its final height. So it's dropping by that distance, and then the final velocity will be square root of 2g h minus h. Okay, so then based on that velocity, right, the final velocity, that becomes the initial velocity of the projectile motion stage. V final equals V initial, right? And then it goes and hits the ground. So then how do we find the range of a projectile based on its initial height and initial velocity? Okay? We can say here x is equal to V initial xt, and then V initial x is simply the same as the V initial, right? That's equal to V initial t, and then we have y final equals y initial plus V initial yt minus half gt squared. In our case, y final is equal to 0, y initial is equal to the little h, right? V initial y, because it's not moving up or down, is going to be 0, negative half gt squared, right? And then I can substitute this t is equal to x over v initial. I can substitute that over there. 0 is equal to h minus half g. And then t is x over v initial, and then you square that. Okay? And then this will give us an expression for the x, the range of the projectile, as a function of the h and the v initial. But we also have an expression for the v initial because the V initial is the same thing as the V final that it had when it went to the bottom, right? So then we can put all of these in. Squared is going to be this equation, right? V initial squared is square root of 2g so we have here 2 over g. V initial squared is going to be this thing, so that's going to be 2g h minus h, and then times h, okay? So I took this V initial, I squared it, and I plugged it into here, and I get here x squared is equal to this. So then the g and the g cancel, and then x squared is equal to 4h times h minus h. How can we maximize this function? So we can take the derivative. As long as I maximize x squared, I can also maximize what the x is, right? So I can say take the derivative of x squared, and that's going to give me what? I'm taking the derivative with respect to little h. So this equation is 4h big H minus 4h squared, right? So if I take the derivative of this, is going to be 4 capital H minus the derivative of this is h 8h. Set this equal to 0, and then you're going to get here 4 big H is 8 little h, and then divide this, so h is equal to big H over 2. So pretty much it kind of makes sense, as long as this is half the original height, that it gains enough of a speed, but it's still enough higher than the ground so that it actually goes and hits the ground at a good distance. So we can give these some numbers. If h was equal to 10 meters and little h was equal to 5 meters, what would happen? What would the range be? So 10 meters is quite high, then it will fall down all the way to the 5-meter line, and then we can use this equation that we derived as a short equation to quickly find the range, right? So we can say here x squared is equal to 4 little h times h minus h. Okay, so then 4 times little h, little h is 5, and then big H minus little h, so 10 minus 5 is going to be another 5. So then that's going to be equal to what? The range will be 10 meters, so it kind of looks like this. Imagine that this is 10 meters, okay, and then this is half of that, 5 meters. So this is 10, it goes like this. This is half of that, this is 5 meters. So then if there was no friction, you would have a really good velocity here. Then it would go like this, and then how far would it go? It's going to go the same distance that it fell from, right? So if that's 10, this is going to be 10, so somewhere over here. It's going to go like this, perform projectile motion, and fall on the ground 10 meters, right? From the edge of the incline, same distance that it started with, okay? So now you can see a good problem that involves some calculus, projectile motion, energy considerations, right? And then finding the maximum range of the block, okay? Thank you very much.